Okay, so in this section, we're going to talk about some properties of determinant. More specifically, we're going to see how the determinant relates row operations and transposes and the product of matrices. So suppose that A and C are n by n matrices. So first of all, if you apply the row replacement, which means you add a multiple of one row of A to another row to get the matrix B. So the determinant of B is the same as the determinant of the original one. And if you interchange two different rows, then you get the opposite of the determinant of A. And if you scale one row by a factor of k, then you can expect that, well, the determinant gets k times larger than the original one. So the determinant of B is the same as k times the determinant of A. And transposing a matrix does not change the determinant. And the determinant of the product of matrices is the same as product of determinant of the matrices. So let's do some examples to see whether all these things are true or not. So let's begin with part B. So let's say A equals to AB and CD, and B equals to CD and AB. So basically I switched the first and the second rows from A to get B. And we know that the determinant of A equals to AD minus BC, and the determinant of B equals to BC minus AD. So this tells you that the interchanging rows will switch the sign of the determinants of the matrices. And for part C, so let's say C to be KA, KB, C, and D. So here I just scale the first row by a factor of k. If you calculate the determinant of this matrix, then this gives you KAD minus KBC, which gives you K times AD minus BC. So this scaling procedure really scales the determinant of the matrix. And now let's consider the transpose of the matrix A. So A transpose equals to AB, CD. Then the determinant of A transpose gives you again AD minus BC, which is the same as the determinant of A above. And lastly, for the row operation, so let's say A equals to AB and C and D. And if you multiply first row by k and then add this to the second row, then this gives you B equals to AB and C plus KA and D plus KB. And then the determinant of B equals to A times D plus KB minus B times C plus KA, and this equals to AD plus KAB minus BC minus KAB. And now this two cancels out. That gives you the determinant of the original matrix A. So suppose that you have a square matrix A that reduced to U by row replacement and row interchanges. So then we get an upper triangular matrix, like what we did in the LU factorization. Then if there are R different interchanges, then the determinant of A equals to, so we know that the interchanging row will switch the sign. So this will switch the sign for R times, and row replacement don't do anything to the determinant of the given matrix. So the determinant of A equals to negative 1 to the R times the determinant of the upper triangular matrix. So here we know that 2 by 2 matrix is invertible if and only if the determinant of A is not equal to 0, but that is indeed true in general. So let us prove this theorem. So suppose that you reduce A to get an upper triangular matrix B. So here, B equals to the reduced row echelon form of A, and E sub i's are elementary matrices. Then there are two different cases. So first of all, if A is invertible, then this gives you the reduced echelon form B equals to I, or A can be reduced to the identity matrix. If you calculate the determinant of B, then this equals to the determinant of the identity matrix, and this certainly equals to 1, and this tells you the determinant of A is not equal to 0. Second, if A is not invertible, then B is not equal to I, but we know that B is a square matrix, so the invertible matrix theorem gives you B has at least one row of zeros, and this tells you the determinant of B equals to 0. And indeed, we could expand the determinant of B along with the 0 row. So this tells you that the determinant of EP multiplied through E2, E1, A equal to 0, or in other words, or if you separate the multiplication, then this gives you determinant of EP multiplied through determinant of E2, determinant of E1 times determinant of A equal to 0. But we know that the determinant of elementary matrices are not equal to 0, which gives you the determinant of A equals to 0. So this proves the theorem 5 above that states A square matrix A is invertible if and only if the determinant of A is not equal to 0.